Okay, so at this stage, we are going to start looking at some familiar applications of symmetry. Again, as physics students, everybody knows these problems. So look at the heading. It says it is obvious from symmetry that. Okay, the question that we are often asked, as in standard physics textbooks, determine the electric field due to a uniformly charged infinite straight wire. Now, this is a problem which all of you know how to solve. You can use Coulomb's law and integration, or you could use Gauss' law, which is what I'm hinting at. So, from anybody in class 12 has studied Gauss' law and these applications. Of course, first year physics, second year physics, you definitely know about this. And the solution, don't worry, I'm not going to work out the whole thing here and bore you with the details of the solution. But the solution starts usually with this statement. It is obvious from symmetry that the electric field is radially outwards. This is the beginning point. After that, you use this and a few more statements which are again quote unquote obvious from symmetry to decide that you will use a Gaussian cylinder here and then calculate the flux of the electric field to the surface of the cylinder and so on, and use Gauss' law and determine the electric field. But what I'm trying to draw your attention to is this. In almost every textbook, in almost every explanation of this, the solution starts, it is obvious from symmetry that the electric field is radially outwards. So, another question. Determine the magnetic field due to an infinite straight current carrying wire. Here, of course, you use Ampere's law to solve for the magnetic field. And the solution starts with, it is obvious from symmetry that the magnetic field is tangential. So let me just point out that these two systems, a straight wire, infinite straight wire carrying charge, and an infinite straight current carrying wire, symmetries. Yet, it is stated almost as if it's in fact, it is stated that it is obvious in most cases that the electric field in one case and the magnetic field in another behave completely differently, and apparently both are obvious from symmetry. Now, I would definitely argue that if it really had been obvious from symmetry, then they couldn't have been this different. I'm not saying that this does not follow from symmetry. It does. It does follow from symmetry. You can use symmetry arguments to argue that the electric field in the first case is radial and that the magnetic field in the second case is tangential. No arguments there. All I'm saying is, despite what your textbooks say, it is not at all obvious. There's a lot of thought which has to go into this and the other statements that are made when you use symmetry arguments. And understanding what exactly goes on in those arguments is really critical to understanding a lot of physical aspects of the thing. So, before we talk about this, let's talk about a problem which, well, of course, I've already said this. How can both these conclusions be equally obvious? The answer is they can't. They're not obvious. They have to be figured out and thought about carefully. But to illustrate what is at stake here, let us look at a problem which is an old problem to anybody who has studied physics at the honors level, let's say, or at the BSc level. This is a problem which was there in a book, in a very favorite book of mine, Griffith's Introduction to Electrodynamics. In fact, it used to be the very first problem in the second chapter of the book. The second chapter is where the physics started. The first chapter was essentially mathematical preliminaries. So in a sense, this was the first problem in the book. And the old version of the book had this in a beautiful way. The question was, there are 16 charges plus q at 16 of the corners of a regular 17-sided polygon. So as you can see, I hope this is visible. There are 16 charges here. I don't need you to count. I've counted. There are exactly 16 of these black dots, which are black circles, which are indicating places where charges are. And there's this one empty corner, which is there, which is shown by this open circle, the unfilled circle. So there are plus q charges at each one of these corners, and you have to find out the field at the center. And what made this problem a favorite of ours in Griffith's old edition is the hint which came with it. The hint said just this much: if you are taking more than 30 seconds to answer this question, you are doing it wrong. End. That was the hint. Well, I hate it that the modern edition of Griffiths has actually changed the question, has broken it up into steps, given lots of steps and so on, given lots of extra hints, and essentially murdered what used to be a wonderful question. So those of you who are studying now will not get the full fun of it. The fun was in the hint, which was there in the older versions. If you take more than 30 seconds to do this problem, you're doing it wrong. That's it. And that essentially told most of us how to proceed. The answer was simply this: if you filled up that empty corner with this red dot here, and put a charge plus q there as well, if all the vertices of a 17-sided polygon, regular polygon, are filled, then the field at the center must be 0. And therefore, the field of the 16 charges, our original problem, plus the field due to this one charge must be 0, the superposition. The field due to the 16 charges must be opposite to the charge field due to this one charge. So it must be 1 over 4 pi epsilon 0 q by r square, directed towards the empty vertex. The field due to the charge here would have been directed away from it. Since that field plus the field of the 16 gave you 0, the field of the 16 must be just this magnitude directed towards the empty vertex. So that was the problem in Griffiths. And a pretty easy one. I'm pretty sure most of you know how to solve this. But now I have a challenge for you. The challenge is the answer to this question, which is taken to be obvious in this 30-second hint of Griffiths. Why is the field at the center 0 when all the vertices are filled? Well, one answer to this would be simply this: if all the 17 charges are there, all the 17 vertices are filled with charges, you would have 17 electric fields directed towards them, towards each one of them. And you can easily add up these 17 electric fields. It's not as difficult as it sounds. After all, you can use the polygon rule very simply to show that they add up to 0. But can you do this without adding up the vectors? After all, if you're adding up 17 vectors, why don't you add up 16 of them and find out the answer directly? Can you find out this result? Can you prove that the field at the center will vanish without adding up vectors? Indeed, without even using Coulomb's law. You don't need any law for this except symmetry. And the answer goes this way. Without knowing anything else, we would say, okay, that is possible. It's possible that there's an electric field component out of the plane of the mirror, and there's an electric field component in the plane of the mirror. But if I rotate the system by 2 pi by 17 or 360 degree by 17, 1/17th of a full circle, what will happen is all the charges will just move to the next slot. So if you were looking at the system before and after this rotation, you should never be able to tell the difference. So what happens to our electric field vector when you do this? The vertical component, the component pointing straight at you, that's along the axis of rotation, that doesn't change. The component which is in the plane, the blue line, that has changed. Now if the charges have not moved at all the charges that were there before Of course, they have moved, but now again you have exactly the identical charge distribution as before, and the point where you're measuring the field, the center, that has also not moved. The electric field simply cannot change. But as you can see, the electric field before was pointing straight at you, one component, another component was this way. Here, the vertical component, the component pointing at you, is still there. The in-plane component is turned around. That simply means that this in-plane component must vanish. There cannot be a component of the electric field in the plane. It has to be perpendicular to the plane. Now you must say, now we have the solution. After all, we know that all the individual electric fields, due to all the charges, are in the plane of the polygon. So since we have now argued that it has to be perpendicular, it must be zero. But I would say that that's really not correct as an argument, because arguing that all the electric fields are in the plane essentially presupposes Coulomb's law. Remember, we are not allowed to use that. We can only use symmetry. So the question is, can we think of some other symmetry operation which will also leave all the charges where they are, and the point where I'm trying to measure the field again at the same place? Then, since the point is the same, the charges are the same, the electric field must be the same. Now there are several other symmetries that you can use here. The one that I want to use in particular here is reflection symmetry. Imagine that this plane is a mirror and you're reflecting the entire system in that plane. What would happen? This is what happens before the reflection. The electric field is pointing straight out at you. Let's assume it's pointing straight out at you. And the blue plane here is our mirror. So if I reflect in this mirror, what will happen? All the charges will stay at the same place. That's the right-hand picture here. But the electric field, which was pointing out, must now point in. So electric field normal to the plane must reverse on reflection in the plane. The electric field in the plane could not have reversed, but that's not there. We have already argued that. So now what happens? If there were electric field at all, it would have reversed, but because the charges are the same, the point is the same, the electric field has to stay the same. So it has to stay the same yet reverse. Now that would mean that it has to be zero. It must be zero, because the only thing which can reverse and yet stay the same must be zero. So that is our argument. So no problems. We have managed to prove something which we all knew. The electric field at the center of a regular polygon with charges at every vertex must be zero. So if you want to say this in a slightly more pompous language, it goes this way. Our system has C17 symmetry. C17, 17-fold rotational symmetry. Remember, the angle through which you could rotate was 2 pi by 17. Then twice that, 3 times that, 4 times that. There are 17 separate rotations you could do, each of which would move all the charges to the next vertices. So your system would have C17 symmetry. Under 2 pi by 17 rotation, the system doesn't change. Neither does our field point move. So this is just a recap in the symmetry language from what our pictures told us. The conclusion was electric field must be normal to the plane. It is also symmetric under reflection in the plane, our system, and the normal component must vanish because under reflection the normal component reverses. So if it has to stay the same and yet reverse, it must be zero. So this was our symmetry argument. So this is fine, and it was pretty straightforward. Now let's see, can we talk about a ring carrying current and talk about the magnetic field at the center? So the system here actually doesn't have C17 symmetry, it has C infinity symmetry. You can rotate it not only by 2 pi by 17 and its multiples, you can rotate it through any angle about the axis, and the ring will stay exactly the same. The point where you're trying to measure the field stays exactly the same, which essentially means that for all these rotations, nothing changes. So the in-plane component of B, magnetic field, must be 0. Same argument as for the electric field. But now comes the point. Reflection in the plane is also, so this blue line, among the two blue lines, this one I know it must be 0, because if it were non-zero, rotating the system would have changed the magnetic field, but it can't. But reflection in the plane is also a symmetry. So what happens when I reflect? Well, remember, this component is no longer there. All you have is this vertical component, or perpendicular to the plane component. And if you reflect, the perpendicular component should reverse, yet stay the same. So what we have managed to prove is the magnetic field at the center of a current carrying coil must be 0. And we have proven this using symmetry, which is one thing which we should not really be able to argue against. Now, of course, all of you must realize that there is a problem here, because if this were correct, then we would have had no civilization as we know it. If you think about it a bit, the very fact that modern civilization at all exists, good or bad, that it at all exists, is dependent on a very large part on the fact that there is a magnetic field at the center of a current carrying coil. Almost all of our modern technology depends on that in some form or the other. So if symmetry really led to this result, that the magnetic field at the center of a current carrying circular ring is 0, then we would be in deep, deep trouble. Well, we are actually in deep trouble, because we have used a very nice argument due to symmetry, and yet that tells us that there can be no magnetic field at the center of a current carrying ring. So at this stage, I want to take a question, I want to ask a question. Can anybody tell me what's going wrong here?
So can I answer?
Yeah, go ahead.
I think the direction of magnetic field depends on the right-handed coordinate system or left-handed coordinate system.
True, but then how do you escape this fact? Yeah. Go ahead.
So the symmetry here, the reflection symmetry doesn't work because by reflecting we are changing the handedness of the coordinate system.
True. Well, your argument is correct in a way, but I would say it's a complicated way of saying something much more simple. So, okay. But anyway, you are right. Yeah, go ahead. No, it won't. We are reflecting in the plane of the loop. If we were reflecting perpendicular to the plane of the loop, that would have been correct. If you are reflecting in the plane of the loop, the direction of motion of the electrons would stay exactly the same.
I think I would better say if I say that the derivation of the magnetic field is from Biot-Savart law, which includes a cross product. And
okay, so what is the issue there?
So the cross product explicitly depends on the handedness. So
okay, you're right. Again, you're right.
Yeah.
You're right in talking about the handedness, but I would suggest that the handed or left-handed coordinate system, while correct, is not the easiest way of talking about it. Okay, so let me just tell you what. Okay, of course that's subjective. I like another language better, and that language is also familiar to all of you. You all know the word. Maybe you have not seen it being used so often, or I have found that most people know the definition of the term that I'm going to use right now, but they don't really appreciate what it means. So let me just talk about that. And we will come about this issue about the cross product and everything. But you're right. You're not wrong. That is very much part of this answer to this problem or this puzzle. Okay, so let's go back to the presentation. And the answer to this puzzle is this: the magnetic field is not a vector. Now, that's a big thing to say, but just bear with me a while and I will explain what this statement means. Well, to understand this, let us think about what happens when you reflect a vector. Imagine that the green rectangle that you see in front of you is a mirror. It's a transparent kind of mirror, so you can see also behind what's happening behind it. And this is one place where I actually miss being able to do this lecture physically, because whenever I try to explain this thing in a classroom, what I do is I ask my students to imagine that the blackboard is a mirror, and I walk across it and walk in front of it and say, okay, imagine that my walking is being reflected in the mirror, and say, understand what happens. So I will just ask you, this is one thing I cannot do now in this online format. So I will ask you to imagine that this green thing is a mirror and somebody is walking in front of it. If this person, let's say me, we're walking from left to right like this, parallel to the mirror, the image will also walk in the same direction, right? Parallel to the mirror. So if you imagine, well, if you think of this as a velocity vector, the component parallel to the mirror stays unchanged on reflection. The component perpendicular to the mirror, if I were to move away from the mirror while if I were to walk away from the blackboard, my image on this blackboard come mirror would move back away from me, right? Component parallel to the mirror stays unchanged, component perpendicular to the mirror reverses. So this is what happens to a vector if you consider both its components. It's easy to think about this in terms of the parallel component staying the same, the perpendicular component reversing. This is how a vector behaves under reflection. So as was mentioned a while ago, a cross product. So what happens when we take cross product of two vectors? Let's say we take two vectors. Right now we are considering two vectors, A and B, which are both parallel to the plane of reflection. Of course, their images AR and BR are the same, right? They stay the same because they're parallel to the plane of reflection. Now what about A cross B? A cross B, of course, is perpendicular to the plane of the mirror because it's perpendicular to both A and B. That's A cross B. However, what happens to A cross B when you reflect? It becomes AR cross BR. A becomes AR, B becomes BR, and they stay the same. So AR is the same as A, BR is the same as B. So what happens to A cross B? The answer is simple. A cross B stays the same. Notice A cross B is directed away from the plane of the mirror, yet it must stay the same because neither A nor B has changed. So this is the first indication the cross product of two vectors actually is very different from a vector. When you reflect, A and B in this case has stayed the same, so A cross B must stay the same despite being perpendicular to the plane of reflection. Well, think of another situation. A is in the plane, B is perpendicular to the plane. So this is what AR and BR are. AR is the same as A, BR is reverse of B. A cross B, of course, you calculate the cross product, has to be in the plane, right? It has to be perpendicular to both A and B, so it has to be in the plane perpendicular to A, P being perpendicular to the plane. But since BR has reversed and AR has not, AR cross BR must be reversed. So notice that what happens to cross product of two vectors under reflection is exactly opposite to what happens to the vectors. For vectors, components in the plane stay the same, perpendicular to the plane reverses. For cross product of two vectors, components parallel to the plane reverses, as in this example, and components perpendicular to the plane stay the same. Now, why is cross product called a vector? We always called it a vector, right? It's called a vector because if you were to rotate your coordinate system, the cross product of two vectors would behave just like a vector. So the components will change in exactly the same way. That's why we call it a vector, more precisely a vector under rotations. So if your world only involved rotations, and if your only symmetry were rotations, and that was the only thing you were interested in, you would not be able to distinguish between vectors and this new kind of object, the cross product of two vectors. However, on reflection, they behave just the opposite as vectors. Whatever a vector does, a cross product of two vectors does exactly the opposite thing. So they are a new kind of thing, not really a vector. They are called pseudovectors, as many of you know, also known as axial vectors. The term vector in the name simply is a remnant of the fact that they are vectors as far as rotations are concerned. But they are really not vectors when you talk about rotations and reflections. In particular, under reflections, they behave differently. So what is a pseudovector? Well, a pseudovector is something which behaves like our cross product a while ago. What happens when you reflect a pseudovector? Well, the in-plane component reverses just the opposite to what our vector was doing, and the out-of-plane component, the one perpendicular to the mirror, stays the same. This is the behavior of pseudovectors under reflection. Okay, and of course, if you think of both components together, this is how the red vector would reflect into this pseudovector. If this were a pseudovector, not a vector. And the answer to our puzzle there was the magnetic field is a pseudovector, and because it's a pseudovector, the reflection in the plane of the mirror does not reverse it. Remember, we had already argued that the magnetic field has to be perpendicular to the plane of the mirror, the plane of the circular loop. Reflecting in that plane would actually keep it exactly the same. And hence, it does not have to vanish. Remember, the only reason why we argued that it must vanish is that it reversed, yet stayed the same. It does not reverse because it's not a vector. That's the real answer. Okay, now, having said this, let us quickly answer the question that I raised at the beginning of this section, which is, why are two opposite things obvious from symmetry? So this electric field due to a uniform straight wire, so imagine that this blue line in the middle of the page is a uniform infinite straight wire. Of course, it's infinite. I've just drawn it as finite. And this black circle is a point in front of the wire somewhere. And the electric field at this point could, in principle, have three components: a radially outward component, which is this line here, a vertical component parallel to the wire, and a cross radial component, the one along the tangent to a circle which you could draw here. Now let's argue using symmetry alone that the electric field has to be radial. For that, we want to find a symmetry which will keep this wire unchanged, that will also keep this point unchanged. Rotation about this wire is, of course, a symmetry, but that will move this point from this place to another place on the same circle somewhere. That's actually a very important symmetry for this problem, but we are not going to talk about that right now. We are talking about a symmetry which will keep the point unchanged. And there's one very obvious symmetry there, which is just imagine that there is a mirror which contains the wire, and there are infinitely many planes which contain a straight line. So it's just one of those planes, but the one which passes through my point. So it goes through the black circle here. And imagine that I'm reflecting in this green mirror. So what will happen? Electric field, remember, is a vector. So what happens to the electric field? the component in plane will stay the same. So these two components, the radial one and the vertical one, they are both in the plane. The component perpendicular is the cross radial one. That one is directed normal to this plane. Okay. So when I reflect, the wire of course doesn't change, it stays exactly where it is because it's on the plane of reflection. The point is on the plane of reflection, doesn't move. What happens to the electric field? These two components stay the same, whereas the one which is perpendicular to the plane, the cross radial component, that reverses. Now this means that if I were to look at the system before and after the reflection, I should be able to say that a reflection has occurred because the electric field has changed. But I shouldn't be able to say that. That's what symmetry is all about. I do a transformation, and before and after everything stays the same, the wire is the same, the point is the same. So I should not be able to tell that I've done this reflection. So the component perpendicular to the mirror, in this case the cross radial component, that must have been 0, because if it were there, then I would not be able to I would be able to tell whether I have reflected, and I should not be able to tell. Well, now I have two components, the radial one and the vertical one. Now imagine another reflection, a reflection in a plane which is perpendicular to the wire, bisecting it cleanly. Remember, this is an infinite wire, so no matter where you place this plane, there will be equal amount above and below. And I've chosen this plane in such a way that it passes through my point. So what happens when I reflect here? Simple, the in-plane component, the radial one, stays unchanged. The outer plane component, the vertical one, reverses. So I must argue again, because I should not be able to tell whether I have reflected or not, the component in the plane, the radial component, must be the one that is non-zero, is the only one that can be non-zero. The vertical component has to be 0. So this is the argument, this is the symmetry based argument which says that the electric field at a point near an infinite straight current carrying wire is radially outwards. Just to illustrate the difference, what happens with the magnetic field and a current carrying wire? So I have a magnetic field due to a current carrying wire here. The current is going from top to bottom. And again, I started with an arbitrary point, and ab initio, all three components, the radial, the vertical, the cross radial, could have been there. I have to argue that two of these components are actually not there. And here the argument, believe it or not, is actually simpler than the previous argument. Just imagine reflecting in this plane. If you reflect in the plane, the current stays in the same, the wire stays the same, the current stays in the same direction, because all the electrons, which of course are moving down here, are actually moving in the plane. So when you reflect, they're moving in exactly the same direction. The current stays upwards, the point stays the same, but now remember, the critical thing is the magnetic field is a pseudovector. And what does the pseudovector do? Both components of the pseudovector in the plane must reverse, and the component perpendicular to it must stay the same. So this is what happens when you reflect. And now we have got to the answer. Because you should not be able to tell whether you have reflected or not, both the components in the plane must vanish. And so the only component present, of course my perspective is a bit skewed in this picture. This is really cross radial. It's perpendicular to the circle that you draw along the tangent to the circle. So that's the obvious from symmetry, that argument. As you can see, it's not obvious at all. It's really reflection symmetry at play here, and the fact that the magnetic field and the electric field behave differently under reflections because one is a vector, the other is a pseudovector. Now this is a critical point, and that's what we are going to use in the next part of the lecture. Of course, once we have established this, the rest of the calculation everybody knows, so I'm not going to worry about that. Now, it's all right to talk about reflection, but we did mention parity at the beginning, also in the middle somewhere. So what has parity got to do with it? Okay, well, parity is actually intricately related to reflection in a way simpler than reflection. Under parity, what happens? Parity is a mathematical operation where a point xyz in your coordinate system gets transformed to the point minus x minus y minus z. So x changes sign, y changes sign, z changes sign. Or you could say, I've just taken all my coordinate axes and flipped them in the opposite direction. So what used to be my positive x-axis is now the negative x-axis, positive y-axis, negative y-axis, and so on. This exactly is what changes a right-handed coordinate system to a left-handed coordinate system, as you can easily check. So what happens to a vector under this? Because all my coordinates have reversed, all the vector components also reverse. So the vector A goes to A under parity and it becomes minus A. So realize that parity is in a sense simpler, always a bit more abstract than reflection. Reflection you can see in your daily life, you can see what happens in the front of a mirror. Parity is more abstract. You don't get to see a parity operation done in real life that way. You don't have a special kind of mirror which will take you and move you to the parity reverse position or produce an image in the parity reverse position. However, describing vectors and pseudovectors become much easier using parity, because under reflection you have to worry about what happens to the in-plane component, what happens to the out-of-plane component, and so on. Under parity, there's just a change of sign. AP goes to minus A. So what happens to the cross product of two vectors? If you have two vectors A and B, both of them are vectors. Under parity, they both change sign. And by the magic of maths, that two minuses make a plus, which we have learned from early childhood, C changes to minus A cross minus B, which is A cross B. It doesn't change at all. So vectors change sign under parity, pseudovectors don't. That's as simple. So under parity, vectors pick up minus sign, pseudovectors stay the same. Okay, now I'm going to skip some of the details here simply because I'm running out of time. By the way, Nobo, can you tell me how long can I go on?
There is another 12 minutes as per we follow our existing schedule.
Okay, so can I go 5 minutes beyond that, or do I stop at 12?
Sure.
Sure what? Sure to which one?
Sure to go beyond 5 minutes.
Okay.
5 to 10
try
minutes.
not to go very much beyond, but then I will cut down a lot of the rest of the lecture. But anyway, that's fine.
Okay.
So I'm just cutting down this part. This is technical, but it just shows that reflections are related to parity and rotations. And now let's answer the question. And somebody mentioned the Lorentz force law. So let's answer the question as to why is magnetic field a pseudovector? The answer is this Lorentz force law is a law of physics. And if we assume that the world in the mirror, which is same as the parity reverse world, is the same, has the same laws as our world, Lorentz force law should be equally valid there. But what happens to Lorentz force law when we do parity? F, now you know that under parity, Q stays Q. That's a scalar, it doesn't change. That's charge. What happens to the force? Force is a vector, of course. Position is a vector. That's really the starting point. Velocity, which is the derivative of position with respect to a scalar, the time, is a vector. Acceleration is a vector. Mass is a vector. So force is a vector. So it picks up minus sign. Velocity also picks up a minus sign. So these are the things which you already know. Charge is a scalar. F is a vector. V is a vector. So they will become minus signs. So what will happen to the equation? If you want the equation to stay the same, F is changing sign, right? Q is not. So if you want the equation to stay the same, E must change sign, but B must not, because here the change of sign is already there through V. So only if you have E a vector and B a pseudo vector will the Lorentz force law stay a valid law of physics under reflections. So now there's a quick thing that I might add to intrigue some of you. All this depends on the assumption in a way that we made that Q is a scalar. Well, does anybody know what a charge looks like when you look at it in the mirror? Is it a positive charge or a negative charge? I'm pretty sure many of you will find this crazy, but let me put this to you. If you assume Q is a pseudoscalar, something which changes sign when you reflect, even then the laws of electromagnetism will stay the same in the mirror world, but then E will have to be a vector and B will have to be a pseudo vector. Sorry, I just stated what is usually the case. If Q is a scalar, this is what has to happen. If Q is a pseudoscalar, E will have to be a pseudo vector and B will have to be a vector. And that sounds absurd, and especially given the fact that we know which way an electric field points away from a wire and so on, you might say that we can easily show that that's not true because electric field is really radial. So we already used E is a vector for that. But I will ask you to think about it. If Q were a pseudoscalar and E were a pseudo vector, B were a vector, you will get exactly the same conclusions that we have reached a while ago. E would still be radially outwards, B would still be cross radial. This is an exercise, just think about it. So the fact that Q is a scalar is more a convention than something which is sacrosanct or physics driven, but it's the obvious convention to make. Why complicate things? Q is a scalar, works wonderfully well. So the assumption that we had made here, we had actually made one big assumption in the previous slide, is we had assumed above that the laws of electromagnetism are the same in the actual world and the mirror world. So in the original and reflected frames or original and parity changed frames, they were the same. That's why we said, since F is becoming minus F, the right hand side also must become an overall minus sign. Prior to the 1960s, 1957 to be precise actually, scientists had assumed that this holds for all of physics, not just electromagnetism, that the laws of physics are the same in the original frame and the reverse frame, actually held for all of physics. That was the assumption before 1957. And if that really were the case, then of course the Ozma problem that we started with would have no solution whatsoever. There will be no way you can convince an alien or communicate to an alien what is left or right without sending him or it an asymmetrical object. This changed in 1957 with the declaration of the results of Madame Wu's experiment. And today, we know that at least there's one corner of physics, the corner that deals with weak interactions, which actually strongly violates this symmetry under parity.